So once we have a handle on that combustion process, on what that equation looks like, we can very easily take that combustion equation and figure out how much air we need, what our air-fuel ratio should be for our engine. And that's what we're going to do now. We're going to take a look at that. And what we're going to calculate is what we call the stoichiometric air-fuel ratio. So that is based on that chemistry equation that we just balanced for the fuel and the air. We're going to calculate ideally and theoretically how much air should go with a certain amount of fuel that's going to that engine. Give us an idea what that air-fuel ratio should be. Now, what you'll find out in practice is that I say sometimes we deviate from that, but really pretty often we deviate from that a little bit. So that air-fuel ratio is not really perfectly, at that stoichiometric ratio. It's going to be off a little bit. It might be a little richer. It might be a little leaner, and we'll do that a little bit differently depending on whether we're in a compression ignition or a spark ignition engine, and we're going to do that a little bit differently because of our fuels, and that is also going to affect our emissions, and we'll see how all that comes into play later on when we look at what kind of emissions, bad emissions gases we get and where they're coming from. So keep in mind that, again, what we're calculating is the stoichiometric, that theoretical kind of ideal ratio, but really we're going to vary that. We're going to deviate from that a little bit in the engines. And we know that, even tuning small gas engines, we'll tune the needle valve a little bit to try to make it run just as good as we can. And there can be a number of things that will affect that. So sometimes we deviate that based on emissions and all this other kind of stuff. And we're going to see as we go through here that the fuel chemistry has a big effect on what that air-fuel ratio is. And with the two examples that we'll do, we'll see that air-fuel ratio can be quite different. And that's one of the reasons why we can't just willy-nilly throw different fuels in an engine and have them operate at their best. So if we're going to change fuels, we need to change that air-fuel ratio. And we'll definitely see that with like our automobiles, that E85, we can't run E85 in any vehicle and have it run well. It's got to be a vehicle that can compensate for that. And we'll show you that in just a second. Now, one of the things that we're going to need to know, that we're going to have on our equation sheet in the back of our minds, are the atomic weights of these fuels. So we have to go back to that. So hydrogen, we know, has an atomic weight of 1. Carbon has 12. Nitrogen is 14. And oxygen is 16. And that's really the only 4 molecules that we're dealing with in an engine. So those are the ones that we got to have. So keep those in your pocket, in your toolbox. This is what we'll have to know as we go through. All right, so let's do an example. So this is one of the ones that we just balanced. So this is gasoline, all right? And remember, we said gasoline is really a mixture of a couple different compounds, but it's pretty close, and it acts pretty close to a C18H18. And we already did this balance. We balanced this equation. We said we needed 12.5 oxygen molecules to go with that fuel molecule. That means that there's going to be 47 nitrogen molecules tagging along with it, going into the engine, into the air. We should get out of it 8 carbon dioxide molecules, 9 water molecules, and hopefully, again, those 47 nitrogen molecules will be going out the exhaust unchanged. We'll see that they won't be, but, I keep telling you that, but we'll come back to it. So what is the air-fuel ratio for this thing? So I'll show you how to do that. And we have to keep in mind is what is the air and what is fuel. So the air is really just the oxygen and the nitrogen molecules. Those 2 molecules is the air. That's the air that's going into the engine. What's the fuel? It's this molecule over here, just this one molecule. So this is the fuel. So this is air right here. This is fuel. All right, so this molecule is the fuel. So when we're calculating this air to fuel ratio, we're going to be looking at those particular components up there. So air on the top, fuel on the bottom. And this is all going to be on a mass basis, on a weight basis. So it's going to be the mass of these molecules. So that air-fuel ratio is based on the mass of fuel, mass of air versus the mass of fuel that has to be going into there. It's not on a volume basis. It's on mass. So that's why we use the atomic weights. So let me show you how to do that. So what is our air? Air, let's look at the top of this thing first. Air is the oxygen and the nitrogen. So what we have to do is count molecules. How many molecules of each do I have in here? So let's look at my oxygen molecules. I have 12.5 molecules, but each molecule has 2 atoms, and I know each atom weighs 16, has an atomic weight of 16. So what is its mass? I have to take 12.5, 12.5, that's the number of molecules that I have. I have to multiply that by 2 because there's 2 atoms in each molecule, and then I multiply that by its atomic weight. What's the atomic weight of oxygen? If you look back in that last slide, it's 16. So 12.5 times 2 times 16, that's what I get out of this oxygen molecule up here. Now, what about the nitrogen? The nitrogen is also part of the air, and I have 47 of those things. So I'm going to add to this, plus I have 47 nitrogen molecules. Each nitrogen molecule has 2 atoms in it. So I take 47 times 2, and then each atom has an atomic weight of 14. So I multiply that by 14. And that's my air component. I got all of my oxygens up here. I've got all of my nitrogens, and they come down here. That's going to give me the mass of air that needs to go into that engine. So divide that now by the fuel. We do the same thing with the fuel. We look at the weight of the atoms in that fuel molecule. So what do I have in my fuel molecule? The fuel molecule is the C8H18. So I have how many? I have 1 molecule, so there's only 1 of these out front. I have 1 times carbon. The carbon, there's 8 carbons. So I have 8 of them. 8 is... The carbon has an atomic weight of 12, so I do 8 times 12. That's my carbon molecules. Plus, I have hydrogen. I have 18 of those. Each one of those hydrogen molecules weighs 1, has an atomic weight of 1, so I'll put 1 down there, even though that doesn't matter. And now it just becomes a calculator exercise. So now I got to watch the order of operations as you're doing this. Multiply 12.5 times 2 times 16. Add to that 47 times 2 times 14. Divide that by 8 times 12 plus 18 times 1. And that's going to give me an air-fuel ratio of 15. And what we usually say, since it's a ratio, we usually say 15 to 1. So this is the way we'll report it. And this is unitless. Okay? And this is the mass of the air, mass of fuel. Mass cancels out. So it's going to be a unitless number. This is just a ratio. So that's the air-fuel ratio. So what that tells me, for every pound or kilogram of fuel that I have going into engine, I've got to have 15 pounds or kilograms of air to go along with it so it'll mix up and burn correctly. Okay, that's my air-fuel ratio. That's how much that I need. Okay, so let's do that other example, and we'll see something pretty interesting happen here. So the other example that we did was ethanol. So ethanol, and when we balanced out that equation, our ethanol molecule was C2H6, and it had an oxygen in it. So that's going to be a little bit different. So this is an oxygenated fuel. We talk about oxygenated fuels. It's got an oxygen in it, so that makes it oxygenated. We needed, along with that, 3 oxygen molecules. That's going to be mean that 11.3 nitrogen molecules are going to be tagging along. We end up with 2 carbon dioxides, 3 waters, and those nitrogens coming out the exhaust on the backside of the engine. Let's calculate the air-fuel ratio. Here we go. Air to fuel. Air on the top. Remember, air is my oxygen and my nitrogen molecule. So those 2 molecules are what constitutes air. So let's multiply this out. Air-fuel ratio. Air is equal to, do the oxygen first. I have 3 oxygen molecules. Multiply that by how many atoms in each one of those molecules. There are 2 oxygen atoms in that molecule. Each oxygen atom has an atomic weight of 16. So 3 times 2 times 16, there we go. I'm going to add to that how many nitrogen molecules are tagging along. I got 11.3. Each one of those molecules has 2 atoms in it, so 11.3 times 2. Each atom has an atomic weight of 14, so there we go. That's my air. That's the mass of air that's going through that. Divide that now by the mass of fuel. The fuel is a C2H6O, so I have in that 2 carbon atoms. Each carbon atom has an atomic weight of 12, so 3 times 12, plus I have 6 hydrogen atoms, so 6 of those hydrogen atoms. Each one of those weighs 1, so I'll put that down like that. But now I also have an oxygen in there. So I have to add to that 1 oxygen molecule. So oxygen there's 1 of those, and it weighs 16, has an atomic weight of 16. And now, calculator, go through that, watch your order of operations, and we end up with a ratio of about 9. So 9, again, we usually report this as 9 to 1. So there we go. So that's the air-fuel ratio for ethanol. It's a little bit different than gasoline, isn't it? If we go back to gasoline, when we calculated gasoline, we had 15 to 1. The ethanol, when we calculated it, was 9 to 1. So what does that mean? For every pound of fuel that's going into that vehicle, I don't need nearly as much air. So with gasoline, I need 15 pounds of air, but for the ethanol, I only need 9 pounds of air. Now we can see why, hey, I can't take an engine, like a small gas engine that doesn't have, that it doesn't have any electronics or anything like that in it, and I've got the carburetor set up and tuned for gasoline, so that certain amount of liquid that's coming in is mixing with 15, a ratio of 15 to 1 of air and going into the engine, it's running well. If I take straight ethanol and put into that engine, it's not going to run well because I've got way too much air. It's set up for all this air in there. So to run ethanol, I would have to retune that carburetor and change that carburetor so that there's not as much air going through, so it's going to burn better. So that's what's going on inside of our vehicle. So if you've got an automobile that is a flex fuel automobile that it can run ethanol or gasoline or any combination thereof, what they're doing in that vehicle is they've got sensors. They've got a sensor in the fuel that figures out how much oxygen is in that fuel, and they're looking at how much oxygen is going out the exhaust, and they're doing balances on that. So they're actually changing that air-fuel ratio. And in those fuel-injected automobile engines, spark ignition engines, they're changing how much fuel that they're adding to the air that's going into the engine. And so they can actually compensate for that on the go. But this is why you can't just switch fuels without having to do some adjustments to make it operate well. So that's what's going on. So there's the air-fuel ratio, how we calculate it, and why it's really critical to engine operation.